Let's get started. Okay, so today we have Savvas, who's been around this whole semester with us. Many of you may have seen him in the sitting in this room next to us. But he is actually a visitor. He does not work here. So let me tell you guys a little bit about his bio. So he got a physics degree from the University of Cyprus in 2012, and after that a PhD from Rutgers. Then since then he's been a postdoc at Johns Hopkins, and right now he's a visiting scientist at UT. And his interests include, but are not limited to, searches for BSM phenomena in LHC and Higgs precision measurements. So take it away.
Thank you, Toa. And I will take this opportunity to first say thank you to Stefan and the rest of the group for having me here as a visitor. It's actually very important for me, and the environment has proven to be very good for my productivity and beyond that. So, and then beyond this introduction, today I'm going to be basically showing results from CMS regarding anomalous Higgs couplings with a focus on an EFT approach. So I know the audience in this seminar is not limited to LHC people. So I think it's fair to discuss a little bit about the LHC. So what you can see here is a blueprint of the LHC. Not really, it's like a map. And it just gives you the scale of how big this machine is. This machine is probably the most complex things that humans have made up to date. Probably, maybe not, but it's really, really complex. And you can see how big it is by the airport here, down here, the Geneva airport, which is a big international airport. And why did we build this machine, and why is it so important? So this machine has these experiments on it, these photographic machines on it, that they basically record collisions. And these collisions can tell us about the basics of our universe and answer some questions that we have about, for example, the matter-antimatter asymmetry that we see in the universe. Maybe we create dark matter. And then, of course, the main thing that we have found with this machine, and I'm going to be talking about today, is the Higgs boson. And this was something that was expected to be found at the LHC. So that's why the LHC was in principle built. And through the contribution of mainly Atlas and CMS, we have observed the Higgs boson. I have also included here other experiments, for example, LHC and ALICE. They are a little bit more dedicated experiments, but still with a very rich physics program. LHC actually might be and is on the forefront of all these lepton violation issues that we see, and these hints that maybe there is something out there beyond what we know. So we found the Higgs, and these are actually measurements of the Higgs boson in different decay modes and also in different production modes. So the discovery of the Higgs was first made in 2012, was announced in 2012, and it was really driven by the gamma-gamma channel and the 4-lepton channel. The plots that you see here are all the latest, if you like, with the updated RAM2 luminosity. And since then, we have a huge amount of significance in what we see. As you can see, the peaks, for example, in the 4-lepton invariant mass is huge, as well as in the gamma-gamma case. But since then, we have also observed the Higgs being produced with a pair of tops with more than 5.2 sigma from a combination of channels. And or, for example, the Higgs decaying to taus. This is another very nice result. And then last year, a very interesting result was the observation of evidence for the Higgs decaying to 2 muons, both from Atlas and CMS. And this is important because this is the first time we saw the Higgs coupling to second generation leptons. So, but beyond the observation of the Higgs, we have now entered a new era. So 2012, now we are 2021. So 10 minus 1 years later, we are actually performing precision measurements with this machine. So what kind of precision measurements? So of course, you want to measure the mass of this object very well. So here you can see results from CMS. I'm sorry to the Atlas friendly people here. It's just what I know better. I'm pretty sure, and it is indeed the case, that Atlas has similar results that mirror this. So for example, here in the bottom left plot, you can see the best to date and the most sensitive measurement of the mass of the Higgs at 125.38 GeV by CMS from a combination of channels. Another thing we did is to check that indeed the coupling of the Higgs to the standard model particles scales with their mass with this beautiful plot that you have seen many times in these seminars, I believe. And then something very interesting is the width of the Higgs. We are at the point where now we can basically restrict the width of the Higgs, not with terrible error bars, but really closing on it. And that is important because the width of the Higgs can tell us if the Higgs couples to invisible things that we cannot see. So you produce the Higgs and then it decays and then you don't see that. This will be very important and it can reveal, for example, about dark matter. So, and since we were talking about the Higgs and LHC, I think it deserves to also talk a little bit about the CMS experiment. Generally, collider experiments have this onion structure. Both Atlas and CMS have this onion structure where you have a collision point, and around that collision point, you build layers of detectors in order to detect different final states. And it's a little bit like a kid's game where you say, oh, this part of the detector light up and this part, so this combination is a photon, while this combination is not a photon, it's an electron. So in the heart of CMS, we have a very granular tracker, and actually that drives the whole sensitivity of the experiment. It's an excellent machine, this tracker, that then combined with the rest of them, with the electromagnetic calorimeter that is targeting photons and electrons, and then the hadronic calorimeter, which is outside for measuring hadronic energy and jets, and then our muons. All these are combined in what we call particle flow algorithm that can, for example, really reduce the pileup that we get from all these collisions and give us very good sensitivity and resolution in the energies of different objects. This is very generic, but yeah. So in this seminar today, going to the focus of what I will be presenting, we have the anomalous Higgs couplings. I'm gonna be specifically talking about results from a dedicated CMS study using the full run-2 data, which is now published. I'm also gonna show highlights from relevant CMS results. And then finally, I'm gonna present a Pheno study that we just put out. We didn't publish it yet, but it's on archive, that can show how you can expand these anomalous coupling measurements. So how do you go and measure anomalous Higgs couplings? So you can do this by looking at the Higgs vertices. So we have the Higgs decaying to things, and then by looking at the momenta of the decay products of the Higgs, you can infer what happened at the vertex. So in the case, what I show here is a single vertex. I'm targeting decay. For example, imagine the Higgs decaying to 2 Z's. And then this diagram here with all these angles is very complicated diagram. Is basically showing the relevant angles that you can measure from the decay. So you have the Higgs being produced from 2 gluons, and then it decays into 2 Z's, the V's, and then they decay into pairs of leptons. And then you can go and measure all these different angles. And all these different angles encode information about the quantum numbers of the Higgs and what happened at the vertex. Of course, to do that, we are going to use the Higgs to 4-lepton channel. This is the focus of this presentation. And we have a large number of events that you can see here over this small background, which is also kind of flat, that we can study. Another thing I want to mention is why is the Higgs to 4-lepton channel important? So as I mentioned before, the discovery of the Higgs was driven by the Higgs to 4-lepton, but also the diphoton channel. But unfortunately, in the diphoton channel, you cannot really measure CP information. And then if you remember the plot, you have a huge falling background where the Higgs diphoton peak lives on. You can also look at Higgs on W. There you have neutrinos. You don't really reconstruct the whole information. But in this specific case of the Higgs decaying to 4 leptons, we have all the information, and you can use it to extract what is happening at the vertex. And on top of that, you have a very flat background that is kind of small. But beyond talking about decay of the Higgs, we are going a little bit in reverse, because this is also how analysis and measurements have been moving. Yeah.
When you say anomalous Higgs coupling, what is the word anomalous supposed to like tell me?
Against the standard model behavior. So we have the Higgs couplings to our standard model particles, and the standard model predicts what this value should be and how they should be. But now we're talking about things beyond that. Like if you go and measure these couplings and you see some different behavior. I'm going to expand on that in a bit. I wanted to first describe a little bit the whole idea behind the measurement. And yeah, but that's a good question. I'm gonna be talking about this in the next slides. So as I mentioned, the way people have been doing measurements is first looking at the decay of the Higgs, but actually you can also look at the production. So instead of looking at one vertex and then looking what happens from the decay products, you can look at the production vertex too, if that production vertex comes with associated particles. So then you can go say, I see the Higgs being created with another jet or two jets. If I take the angles between these two jets, can I infer something that happened on that vertex? What is interesting is that, of course, you can have interference. And that is very valuable because interference in quantum mechanics is information, which you can use to increase your sensitivity. But it also increases the complexity of the measurement because you need to take into account all the interference terms that exist. So then in this analysis, we basically study the production of the Higgs with these 4 modes that I described here, also TH actually. So we have gluon fusion, which is a dominant. I say dominant because it has the largest cross-section. Then we have VBF, vector boson fusion, either 2 Z's or 2 W's fusing, giving you the Higgs. We have VH, which is the so-called associated production. You produce the Higgs, and then a Z is radiated on the side, or a W is radiated on the side. And then also TTH, which is important for studying the fermionic couplings of the Higgs. So I mentioned how we are going to produce and study the Higgs, but then we also need to talk about effective field theory before we talk about the anomalous couplings themselves. So unfortunately, the LHC has not given us clear indications of BSM phenomena. For example, a new particle with a 5 sigma significance. So people have now turned into these new ways of looking at the data from the LHC. And one of them is this EFT, which is a general approximation tool. So imagine that we have these couplings of the Higgs, and we have a very heavy resonance that actually affects this coupling through a virtual loop. What you can do is that you can parameterize this contribution by an operator, and then use also a cutoff scale where you say, I don't care what happens about that scale, but then you can study the contributions from these heavy particles in these couplings using EFT basically. Yeah, so that's the main idea. It's like doing an expansion in energy, and I'm gonna cut off some terms, and I'm gonna look at these operators, how they affect the couplings. So, and coming to anomalous couplings. So what you see here is the scattering amplitude of the Higgs to fermions and to bosons in the so-called mass eigenstate basis. So on the top, you see the coupling of the Higgs to fermions, where we have kappa F and kappa tilde F. Kappa tilde F would be a CP violating CP odd coupling, while in standard model, you only have this kappa F, which is actually equal to 1. In the case of the VV couplings, which is the main focus of this talk, you can write the full amplitude up to dimension 4 and 6 in energy, where you have these A1, A2, A3, and these lambda terms. These lambda terms are cutoff terms. Then we have A3, which is our CP odd coupling, and then A2, which is a CP even coupling that is not standard model though. And then we have standard model, which is A1. So in the standard model, what you should see actually is only this A1. And then we can go and look if we find anything from the rest. This seems very complicated. And then we have our indices, our V's, where you can make any allowed combinations of your vector bosons and also your bosons. For example, photons, Z's, W's, and gluons. But then if you start thinking about symmetries that exist in the standard model and other considerations, you find out that many of them are reduced. And then if you do that, and you reduce them, you can also relate them with a Lagrangian. And then you can talk about the couplings in a Lagrangian instead of these amplitude couplings. So, and this is all of them here, basically. So here we have the standard model coupling. Then we have G2 is again a CP even non-standard model coupling. And then this G4, this Z, for example, is CP odd one. And then you can see the rest of them here. It's many couplings, but yeah, I mean, we will talk about them more. So one of these symmetry considerations that you can think about is SU2 cross U1 symmetry, which if you think about it, it enforces these relations between the anomalous couplings. So from these 13 ones, you end up with only 5 independent. Actually, what we have done is that we have enforced different schemes on how these couplings are related. So the first scheme is the one that we equate the W and the Z couplings, and we also do not consider any gamma-gamma or Z-gamma couplings. And this gives us 5 independent HVB couplings. And let's name this EFT type 1 or non-symmetric. This is one of the type of measurements that we do. You can go a step further and then say, I'm actually gonna relate my couplings differently. So I'm gonna take the standard model Weinberg angle value and plug it in. And then you end up with 4 independent couplings. And this setup we name SMEF. Under this setup, you can go look at the Lagrangian coefficients. And then we are left with only 4 Lagrangian coefficients from this very, very complicated Lagrangian that I showed you in the beginning. You can only talk about these 4 and study these 4. Of course, we also have, so these are for the ZZ couplings, the WW are related to the ZZ, and then we have also the gluon couplings. The photon couplings and Z gamma couplings in this study were considered very well constrained, and so we didn't study them. I hope I didn't lose you. I know it's a little bit complicated, but it's not as complicated as it seems. So how do we measure these anomalous couplings. So what you can do is that you can go see your signal strength. You go say, I'm going to make an observation. How many events do I see? And how many do I expect? And take a ratio. Or you can and then you can either measure the ratio or directly try to measure couplings. So signal strength is defined as this mu, which is just a ratio of yields, if you like. And then what we do is that we try to say, okay, given a yield, how much contribution do I get from a specific anomalous coupling? So we construct these so-called FAIs, which is basically the coupling value times a cross-section ratio over the total cross-section. This cross-section ratio is defined as the anomalous coupling cross-section over the standard model cross-section for decay. And here you can see some of these values for this. So here you can see the couplings that we are considering: A3, A2, kappa 1 Z gamma, or lambda 1 Z gamma, as we name them. So then you can find the corresponding, you can define the corresponding FAIs, and then you can go do these measurements. Why do we do this? Because we don't need to worry about the total width of the Higgs. Many systematics are actually cancelled in this ratio, and you don't need to worry about them. And also, this FAI quantity is very well bounded between -1 and 1. So then the second type of measurement is directly measuring yields and trying to relate them to the couplings. But for that, you need to worry about the total width of the Higgs. So why do I need to worry about the total width of the Higgs? Because the total width of the Higgs would be modified by the presence of anomalous couplings. So if I want to go and measure how many events I have and directly link it, I have to take into account the modification. And so this is what we did. There is a study that we did with the people at Hopkins, where we extracted how this total width of the Higgs changes with respect to the presence of anomalous couplings. And we wrote out analytical formulas which go into the calculation of this width. And then once you do this, you can interpret this in the Lagrangian coefficient language. So this was basically the blueprint of how to parameterize and then perform measurements of these anomalous couplings. But of course, there is a whole experimental aspect to it of how do you use your events to do this. So our analysis is heavily based in the main Higgs for electron analysis, which is basically measuring the cross sections in different beams of PT and eta of the Higgs. This is the so-called STXS analysis. And we use the same objects with them, the same data samples, and the same background estimation. I'm not going to go in a lot of detail about that because I think there are more interesting things to talk about, but we could talk about that. Then the difference with them is that once we have our objects, for example, our electrons, our photons, our Z pairs, you try to calculate the mass of the 4 electrons, for example, as you see in this plot. What we do is that we create 2 schemes where we categorize events. The first scheme is to target the fermionic and gluon couplings of the Higgs. And the second scheme is to target the VV couplings of the Higgs, meaning ZZ, WW, and Z gamma. Why do you need these 2 schemes? Because in the first case, you really want to target TTH production. That vertex is really going to tell you what is happening between the Higgs and the top. In the second case, you want to target VBF, VH, and gluon fusion, for example. So what we do is that in order to categorize our events, we use this matrix element-based discriminant, which, so you take a matrix element, you plug in the observables from the experiment, and that thing tells you what is the probability of this event being VBF production, ZH, gluon fusion, TTH, and also standard model or another anomalous coupling. And using this, we categorize our events. And I think I mentioned this, but the main reason why, for example, in scheme 2, we have 6 categories, or in scheme 1, 7 categories, is to separate the different production modes, because each one has a different value in terms of measuring the anomalous Higgs couplings. So once we categorize our events, we go a step further. And then what we do is that we construct our observables to extract either the FAIs or the couplings. To do that, again, we use this matrix element-based discriminants. So as I mentioned it before, you have your observables, which is these angles that you get from each of the diagrams, the angles between the z directions and the Higgs, the masses. What happened?
I'm not sure.
I'm pretty sure I'm sharing. Though,
Yeah,
so
you're
it should be
fine. There we go.
Yeah. So, and then using them, you plug them into the matrix element, and then you can take, you get out as a value these probabilities. So we have different kind of discriminants. The one kind is to separate any kind of signal and background. We call them B background. So you just plug in, you get a probability, and you separate background and signal. The other kind of discriminant is this D alternative, which is designed specifically to separate between your standard model and another kind of hypothesis. For example, a coupling that violates CP. And then the third kind of discriminant that we have is the one that tries to extract this interference information that I talked you about, which is actually very important. I'm just gonna say that actually there are many discriminants. For example, many discriminants, and for each of these many categories, different are used. And I'm saying this because you need to think carefully what you use in each time. For example, in the VBF 2jet category that we have, which targets events where you have VBF and you manage to reconstruct the 2 jets, you want to use both decay and production information to calculate these discriminants that you have. So, for example, here you have interference terms between CP odd and CP even, and then individual standard model against pure anomalous couplings. So we have lambda 1 z gamma, we have lambda 1, we have our CP odd, and then our CP even anomalous coupling, and then also even against background. So this is just an illustration of how this is done. And then what you do once you build these discriminants is that you build templates. And then from these templates, you go and you create feeds, likelihood scans of the data. So the number of templates really depends on the EFT type that you actually choose, because in the EFT type 1, we have more couplings, and that's meaning that you need to consider more contributions, while in the second case, things are connected with each other, and this reduces the number of couplings. And this is something of a trick, which is, imagine if you need to create 17 different signal contributions. Imagine you are doing a resonance searching somewhere, and you need to actually include 70 signal contributions. Can you imagine doing a full simulation of that? It's simply ridiculous. So what we do is use a trick, which says that if you have the same initial and final state, you can take that event that you generated and reweight it to a different kind of signal. So this is a technique that has been used extensively, not only in this analysis, but also in previous Higgs analysis. So since all our signal is going to create the Higgs through gluon fusion and then decay to 4 leptons, we generate standard model or an anomalous hypothesis, and then we reweight it into all these interference components and the anomalous contributions. So yeah, this is an important aspect actually. And once you do that, you take all your templates, you take your data, and you perform a multi-parameter fit, and you extract your FAI scans. So I'm gonna start showing results from these measurements. And the first thing I'm gonna do is show you results with respect to the Higgs couplings to gluons and fermions, at least from what we can do in our analysis. At the top, you can see measurements of the couplings of the Higgs to gluons. We have two parameters here. We have the signal strength and Fa3GGH. And to demystify how this is done, you basically go and look in the category where you have tuned jets, which is what we call VBF tuned jet category, if you like. And there you will actually see a strong gluon fusion contribution. And you might wonder why. Well, gluons can radiate. So instead of just gluon fusion to Higgs to 4 lepton, you can have gluon fusions, gluons radiating tuned jets, and then they go into that category, and you can use that to measure what is happening in that coupling, in that vertex. And then what we do is that once we do our measurement, we measure basically the CP odd component with this Fa3. We can convert it into the Lagrangian couplings, and the mu sets the radius of this ring, and then the inside of the ring is actually resolved by this Fa3 measurement. The second type of measurement in terms of fermions that we can do, that was gluons, of course. Now, in terms of fermions, is to go look at TTH events and study the couplings of the Higgs to top. And this is what we do. And we don't just do that in Higgs to 4 lepton. Once we do that in Higgs to 4 lepton, we combine it with Higgs decaying to photons. There are some assumptions that you need to make about contributions in the decay side and how you can combine things. But then you can, if you do all this, then you can interpret the results in terms of the couplings of these kappa couplings to the top, our CP even for a standard model value of 1 and CP odd, which should be 0 unless we see evidence of CP violation. And then what you can also do is assume that the gluon fusion loop is dominated by tops. And instead of just looking at TTH that goes to photons or leptons, you say, I'm going to also look at gluon fusion, and then I'm going to assume that what happens in the gluon fusion loop is actually because of tops. And then you can do a combination of measurements. Actually, what is interesting is that the 4 lepton case prefers a negative CP odd contribution, but once you combine it with gamma gamma, that goes away. And also the other thing is that there are not so many events in the case of TTH that contribute to that. And if you see, it's still consistent with standard model within 1 sigma in this likelihood scale. And you can also again go and do an interpretation in terms of top couplings. I will mention that there are even more results in terms of fermions and gluons that we have studied in combination, but I don't think this is the focus of this talk. I really want to show you HBV couplings. Okay, so talking about HBV couplings, the first thing that we do is that we go and we study the couplings of the Higgs to the Z's and the W's using this EFT scheme 1 that I described that has more free parameters. And then you can see here the CP odd, CP even, and then these cutoff scale contributions, the scans of them. We do 2 types of scans. One where in each case, all the other anomalous couplings are fixed to 0. And one where you let them free and you float them. So in a way, you do a multi-parameter fit. In the case of multi-parameter fits, as you can see with the solid red line, we have some cases where the likelihood minimizes away from 0. Of course, there is still this strong valley that is consistent with 0. But for example, more data should show whether these are real minima. And what do they mean? And then you can also go and instead of do these 1-dimensional scans, you can put them together. you scan two parameters at the same time and let the others float, of course. And you can see here where this minima that I described before live. But in all cases, there is always a small island at zero that goes down and tells you, okay, standard model is still included. Don't get too excited. So then I'm going to show results with respect to EFT scheme 2, where we actually relate all these couplings together. In this case, I remind you that you are allowed to do this interpretation to the Lagrangian couplings. And again, I'm going to show two types of scan, one-dimensional and two-dimensional. So in the EFT type 2 case, or SMEF, where there are the relations, we have less free parameters. So we have our CP odd, CP even again, and lambda 1. We don't observe the picture that we observed in the previous case, where when you float the scans, you see minima away from zero. The minimum is at zero. What is another interesting thing here is that production dominates the results. So these values that you see at zero actually come from the production information, which is interesting. People, yeah.
I'm not super familiar with the terminology. When you say float the scans, like
Float the other parameters, yeah. So you can either go and say, I'm gonna make a template fit where the other anomalous couplings are fixed to zero, or I'm gonna go and scan the specific anomalous coupling and let them float. So then I find a global minimum in a way. And that is a less constrained scan, but it's also a little bit more correct, because in nature, you don't do, in nature, nobody guarantees you that a thing is fixed to zero unless you measure it, right? And in some cases, we do fix things to zero. I have a long list of results here. So approach 1 and approach 2, where you can see, as we just discussed, things fixed to zero or floated, and they are observed values and what we expected. Fortunately or unfortunately, everything seems consistent with the standard model in this. Yeah. So then what we do is that we go and we interpret our results in terms of these Lagrangian coefficients. For example, this delta CZ is the modification to the standard model G1, and it's close to zero. The rest of them are 2. But why do we do this? Why is this important? This is very important because what people want to do at the end with all this is make a global fit. So we do our Higgs 2-4 lepton studies. People do their diphoton studies. People also study ZZ couplings, not Higgs ZZ couplings, but even the couplings of the Z or either kind of couplings. And you can relate all these things together under a big umbrella and then make a big scan, if you like, of these parameters. So in order to go into that direction where you can do these grand combinations, people are using specific language on how these couplings are defined. And so, for example, there is this Warsaw basis. We are using the so-called Higgs basis. But once we go into the Lagrangian couplings with this interpretation, you can actually go and translate them in this Warsaw basis. I might mention a little bit about this in the following slides. And here again, I have the Lagrangian couplings to these scans where the rest are floated. Again, everything is consistent with the standard model. You can see some interesting correlations. Yeah, but nothing that we do not expect. So as I mentioned, here you can see a table of all the coupling results in the Lagrangian picture. But you can also do this translation that I mentioned to the Warsaw basis couplings, and we have a list of those here. So yeah, I was going to mention that in the Warsaw basis, for example, you have a ridiculous amount of couplings. You might think this is already crazy what we do, but it's even more crazy there because they actually use different bases. So what happens is that with the Higgs bases, it seems that we managed to reduce the number of couplings because they find, Atlas, for example, uses these Warsaw bases, and what they find is that their couplings are highly correlated. And so you end up with linear combinations that are like your principal components in this. And they come close to what the Higgs basis is, which is the mass eigenstate basis, which is driven by what the masses of the particles are. But again, I mentioned this because that's why we put the effort to do this translation into these Warsaw basis couplings that will allow us in the future for global combinations. So beyond these Higgs 2 lepton results, I'm going to mention some extra stuff. There are two more analyses from CMS that I want to mention. The first is an off-shell measurement of the anomalous coupling. So what we have been talking up to now is going and finding the Higgs on the Higgs mass with a mass window, 105 to 140 GeV, and whatever I see in there, I feed that and I do my results. You can go in off-shell and you can study what happens there. So this result was the first measurement of anomalous couplings in off-shell. I wasn't personally involved in that, but this is from CMS and from our group in general. And then what is interesting there is that there is an interplay between the width of the Higgs, which you can measure in off-shell, with the anomalous couplings. So in this specific result, there was a multi-parameter scan of not a multi-parameter scan. The width and the anomalous coupling were floated at the same time to do the scan. Okay, so maybe it's important to mention here that the reason why off-shell allows you to measure the width of the Higgs is that in on-shell, you have a dependency on the width of the Higgs, while in off-shell you do not. And so you can take a ratio of the yields of what you see in off-shell and on-shell, and this way you can extract the width of the Higgs. Another approach different from that is to go and feed the peak of the Higgs, but that is a terrible method actually. And this gives you very good resolution. So, but as I show here, it's also sensitive to anomalous couplings. The second result I'm going to show is a measurement of anomalous couplings from the Higgs decay into a pair of taus. In that case, they use the production information only, and they don't look at the decay. They just use the decay to tag their events. And then you get these beautiful scans. And actually, they did a combination in the past with a previous Higgs 2 lepton result. And then here, there is a summary of different anomalous coupling measurements from HVV measurements. This is a little bit dated, but still shows the picture that certain things are well constrained, some things are not, and we're improving the picture. Yeah. And I see that my time is running out a little. So yeah. I want to talk about another thing before we close this seminar, which is moving ahead. So we published 1 week ago, a Pheno paper where we are studying anomalous Higgs boson couplings and how you can use virtual photons to study them. And this was done with people from Hopkins. So if you remember here, when we were describing these relations, I had these terrible red lines and I was crossing out things. So these are the photon couplings of the Higgs. So we have Z gamma and gamma couplings of the Higgs, and we are only looking at these things. So and why did we do that? We did that because first of all, these couplings are well constrained from direct Higgs decays to photons and Z gamma. And the second, well, that was the main reason, and so we just constrained them. But there are some issues there. The first thing is that if you do that in gamma, you cannot really extract information about CP information. Yeah, so we decided to go and check what we can do here. So we started studying how these anomalous couplings affect, for example, your dilepton masses. So you have the Z or the photon being generated from the Higgs and then the decay into lepton pairs. So you can go reconstruct the masses what you see here is that, I don't know how well you can see, but the blue line, for example, is really high in the low masses for the M1. And then again for M2, M1 and M2 is just the hierarchy in the event of what you call high mass and low mass in this pair, in these lepton pairs. So these anomalous couplings have a strong contribution at log 2 square. So what we want to do is study the sensitivity to 4 leptons from these virtual photons, where you have the Higgs decaying to virtual photons that decay to leptons, and you measure this. And we also want to study the sensitivity from production information, because this is something that nobody did before. And this is a FINO study, so we also looked at projections to how the high Lumi LHC, what the high Lumi LHC will be able to do. So again, to do this, we construct these discriminants, dedicated discriminants, to extract these anomalous couplings. We try to use either decay or production, or a combination of the two. We do not consider any of the old ZZ, WW couplings that we mentioned before. And we apply some cuts. This is important, and it's relevant also to the people here at UT. So we actually apply a 12 GeV dilepton mass cut. So if you look at here, we basically cut somewhere here. We are killing a large part of the anomalous contributions. The reason we did this is limitations from CMS. Of course, this can be improved, and this is something also that we want to look at. And there are benefits to this also, to the type of measurements that Stefan is doing with Himal and the rest of the students. So results. Here we have results of our FGs compared to our FA3, for example, for ZC. So again, we parameterize our FAIs as a ratio of cross-section times coupling squared over the total contributions. Why did I put this together? I really wanted to show you the difference between the shapes. If you see here, this is from the ZZ result for CP odd. You get a very beautiful valley close to 0, which was actually driven from production. So the VBF and VH cases are very, very, very sensitive to the anomalous couplings. While in zinc gamma and gamma gamma, that is not the case. And the reason is just what the cross sections get modified as. In the zinc gamma and gamma gamma case, the cross sections are really modified from anomalous couplings in the decay side, while in the ZZ, they are really modified in the production side. So this is what you get. And of course, this drives the whole structure of the likelihood scans. So these are the actual results. Before, it was just a comparison with ZZ. So you can see here the zinc gamma and gamma gamma scans. Decay, as I mentioned, dominates. Decay and production is the red, production is only blue. There are some asymmetries that we see that are actually expected. I mean, in the minus and the positive and the negative side. And then the Higgs zinc gamma couplings are not as tight as the gamma couplings, which is not surprising. Then what you can do is, again, convert this into direct coupling scans. But again, here you need to consider the modification of the total width of the Higgs. So this is something that we put effort to calculate how these things change. And again, check both production and decay. So here you can see results from production only and decay only, sorry, production and decay. As you can see, the scans at the bottom are way more sensitive. You can compare them directly. But I should mention that even though production doesn't seem to contribute much, you could use multiple decay channels, as we did with Higgs to tau tau, for example, to enhance production information. So you could use multiple decay channels and then study production side. and then something extra. These couplings can also modify the associated production of a photon with the Higgs. And this is important because it's a little bit like the studies that Stefan is doing, where you are searching for something very, very rare. So in this case, the standard model expectation for 3-atom burn, if I'm not mistaken, is 0.1 events for an actual signal event. But if you have anomalous couplings, that thing will be off the roof. And so we went and studied that. This is something that nobody at the LHC has measured yet, trying to find a Higgs and a photon in the same event. We applied some basic cuts on the photons in order to suppress background, which you can very well suppress just by the fact that you are trying to find photon, Higgs, and the Higgs decaying to 4 electrons. So that is really pushing things down. So then we went in and we checked again our coupling scans. They are not as tight as from the 4-electron case production and decay, but they are still important. So this is something that we really look forward to incorporate in a future CMS measurement. And then I mentioned that there are reasons why we didn't look into these couplings before in Higgs 19009, the published CMS result. And the reason is that people have went and looked at the yield that you get from Higgs decaying to photons and zinc gamma directly, and they measured these results here. So, and then what we did is that we said, okay, this R zinc gamma, which is the ratio of the yield to the standard model yield, how does it depend on the CP even and CP odd couplings? So they were just measuring how it changes, not how it depends on it. So we parameterized that and we converted into likelihood scans of a way, an analytical likelihood scan. And you can see how tight the constraints are. They are very tight. But of course, there is no CP information. And so you get this ring of degenerate minima. Well, you can go and take your 4-electron events and your Higgs to gamma gamma and zinc gamma events and combine everything together. And what do you get? Well, of course, the gamma gamma and zinc gamma are more tight, but the 4-electron information allows you to resolve what happens inside this loop. So if you see here, this is a picture from the previous slide. You have all these degenerate minima. You don't know which one is the one that actually is the true minimum. Well, here you can actually resolve that. If you see the blue is only here. And even in the zinc gamma case, the ring is more blue on this side than this. It's not anything crazy, but yeah. So we believe that there is value in using a combination of 4-electron information and Higgs to gamma and gamma, where you also include, for example, gamma H to do this kind of study. Okay, and this is the end of my talk. So I have shown you results from CMS for a dedicated anomalous coupling measurement of the Higgs. There was, I tried to explain how we perform EFT interpretations, why EFT is important. As you have seen, CMS is really pushing in terms of precision measurements. And we try to restrict BSM phenomena and also measure the qualities of the Higgs very well. The anomalous Higgs couplings are well constrained, but there are still places that we can look, and there are still things that they haven't been looked at. EFT with these grand combinations can provide like a big net search that you try to see indirect evidence of something. You will not just see a peak in a mass distribution, you will see really something else. And let's not forget that what we have actually done at the LHC is that we have only analyzed a few % of the available data set that we are expected to have. So who knows what we will find. So thank you.
Okay, thank you very much. All right, who has questions? Let's start with students.
In the discriminant translation, like you discriminate with the male or for the signal and the diagrams, and within signal, you discriminate, you apply for the standard model like and non-standard model like. For the non-standard model like, there are a lot of theories. So how dependent you discriminate on those theories?
That is the beauty of this kind of parameterization. Everything new, well, with the caveat that we're looking at this kind of operators, should be described by this. It should be hidden by this. So then by looking at something that looks like an A3 or an A2, we can, that's the thing. So this is the beauty of EFT in a way, that it hides under the carpet all the different details, and then you get contributions with different operators. And I think that is also why it is important to make these floated scans and not just fix other anomalous couplings, because a new phenomenon might not manifest clearly as A3 or A2, it might be a combination. So that's why you need to look.
Yes.
I had a similar question. I don't know if you have like anything more to add, but like when talking about beyond standard model physics, is supersymmetry still the prime theory that you would look towards, or like you said, you're completely ambiguous to anything?
Well, in terms of these couplings, things are ambiguous. So any heavy resonances will just appear as corrections to what we see, not corrections, contributions to what we see, and we will see scans shifted outside the standard model. Now, about SUSY specifically, I won't say I lost my belief in SUSY because it's a belief, but the main motivation for SUSY was to explain, for example, the light Higgs mass that we observed. And well, the new SUSY particles should have been laying close to where we are searching, and unfortunately, we didn't find them. But who knows? Maybe they are hiding there and we just cannot find them. So, yeah. I think especially with the lepton violation universality signs appearing, people are moving towards vector-like BSM contributions. It's not my expertise, but I think many people are going in that direction.
What does that mean, vector-like contribution?
You have particles that have they couple. I don't actually know all the details, but I know that they behave in a very weird way. It's like carrying the lepton flavor and also coupled to QCD. Am I wrong? I don't know. I think it's something like that.
Well, the vector-like is about how they like transform, but I think it depends on specific, but there are multiple versions.
Yeah.
I think you're referring to leptoquarks,
Yeah, leptoquarks. Yeah, for example. Yeah.
which carry both baryon number and lepton number. Yeah.
Exactly. So then, but then you also have like all these non-standard searches that are very important. For example, displaced things, long lifetime things, rare searches. There is this whole effort in CMS with the jet substructure because we don't know what is hiding under the QCD blanket. Yeah.
Here, if production of gamma H, you said like 0.1 event signal event expected in 3 that highly UCD LSC. And you said if it do not follow standard model, there is expectation of huge number of events. So let's say if it do not follow standard model, how many events?
That's a good question.
Something in run two?
I think there was something even in run 2. I don't remember what was the sensitivity to run 2. I think in the paper we actually quote signal events that we would expect. I don't remember them on top of my head, but I can look at it. And of course, that depends on how you do your analysis in terms of your photon selection, and if you, what kind of PT cut you apply.
Are there any, you mentioned interference a few times. Are there any like specific, maybe reasonably well-motivated interference scenarios that would make it so that this just doesn't work? Because I guess it's probably unlikely that you would cancel out corrections to all of these parameters that you're looking for at once, or is there a scenario in which that might happen?
So actually what we do is that we include all interference effects, and the interference effects, they couple as the pure anomalous contributions will couple. So, so it's literally expanding this amplitude here. So then you can get A1, B1 terms, and these are what we call interference terms. Some of them are negative, and they can cancel out things. But all these things have to couple the same way between your pure anomalous coupling terms and these interference terms. So yeah, I mean, I think in that way they are well explained and understood, and no, you cannot have cancellation effects that way.
Not a large enough negative contribution in any reasonable.
Yeah, in some cases they are big negative contributions, but they will scale with the anomalous coupling. They have to have a G factor in front of them. So if you would have standard model plus anomalous coupling, you will have standard model square plus standard model times your anomalous coupling with an G anomalous in front of it, and then plus the pure term square. So that those two G's talk to each other. They are bounded together. So
Other questions?
Anybody?
Anybody?
Go ahead, Stefan.
Oh, I wanted to ask him something heretic. I wanted to ask to maybe for the benefit. You said it's a terrible idea to measure the total width. You mean it's a terrible idea to measure the total width at the LHC. But if somebody gives you enough money to build a lepton collider, you can measure this with very high precision. At that point, you're doing the other exercise, no? You're doing the exercise, adding partial widths together. In this case, allowing them to be complex. So some of it can squeeze away. But in the end, when you add up width, you add up real numbers together, and they have to add up to the total width. Are you doing this? Yeah.
I agree. And to be clear, I said it's a bad idea to measure the total width of the Higgs on shell only by doing a mass spectrum fit. But yeah, I agree with you. Yeah, if you have a dedicated Higgs machine with a very good resolution, you could probably do it. And there are analyses from CMS that try to restrict the width of the Higgs in on shell.
But no matter what, you're never going to get a direct measurement of the Higgs width, even at a lepton collider, that competes with the precision of an off-shell measurement, right? I mean, it's a couple MeV. You're not going to have mass resolution like that, right?
No, you can. You have
but
some
again,
5
from
MeV.
indirect.
Right, but the additional sensitivity comes from the fact that you measure interferences combined with angular distribution, or which are defined through angular distributions. That gives you this sensitivity. My point being, that might be fine, but in the end, you add up the contributions. And if you have a below or at the level of MEV resolution, then you may get it. But nevertheless, what you measure here already is very close to the standard model value. Just, yeah, you show it here actually. Exactly.
And this is from
maybe this is off-shell. That's your off-shell measurement.
Yeah, this is the option. I think the on-shell measurement, the error, if I'm not mistaken, is some GeVs, no?
Oh yeah. No. At this point, we don't even talk about this. I mean, like I said, if you have infinite money now to build this thing, to measure it, but the standard model prediction, if you were to indicate it just for the benefit at this point, was the the best calculated standard model value right now? If you were to put it on top.
4.1 MeV.
Yeah.
I don't know about the errors here. I mean, the errors I think are not theoretical. It's from our.
No. But this is your measurement, and then we have a prediction. I just wanted you to.
I think that's got the black lines and the.
Oh,
yeah. The observed. So okay, we have to be careful here. The observed is of course what we observe and what they observed. Actually, I didn't do this analysis in Higgs 18002. Expected is the expected sensitivity centered at the theoretical, of course, value, which is what you mentioned, Stefan. Now, what is the error on the theoretical value from theory? I don't know. It must be very small, right? But this expected is from this, like if you do just a toy sensitivity study on the width of the Higgs, yeah.
Yeah, right. No, I meant really the calculated value, so one gets a feeling.
I would expect that to be really smaller.
Yeah, I would expect that also to be really small. I mean, we think standard model, of course, right? Yeah, we're talking about standard model. Yeah.
Do we still have time for a quick question?
Sorry.
Yeah. So any interpretations that you make in an EFT coupling space are going to be sensitive in some way to your choice of lambda, your cutoff. But I didn't see a specific named value of the cutoff throughout these studies. What are you assuming in that?
We push it high. We actually push it high, like above 10 TeV in combination. I think actually that lambda appears as lambda squared, and we put the 100 GeV on it. Yeah. So if you do the math, it's 10 TeV or something, if I remember.
So then the thing, and this is, I think, purely a matter of interpretation. Then what you're saying about the couplings in setting, for example, limits on BSM models is these are limits on BSM existing above 10 TeV, right? Like. That's where these effective couplings will actually kick in.
Dependency of the results are to this cutoff. I don't know how that exactly gets translated into our sensitivity. And that's a good question. I will need to actually think about that. That's a very good question.
Was there a reason that it wasn't set to, some factor times the Higgs VEV or something like the end of the standard model scale?
I actually don't know. I don't know.
Okay. Thanks.
But I will look into it and yeah,
it'd be interesting.
Okay, I think we're well over time, so I'm going to cut it off now. So thank you so much, and it was great to see what you're working on.
Yeah, I hope I didn't bore you to death.
No, it's very interesting.
Okay, thank you.
Thanks again. Okay.